Are you looking for a professional and efficient robotic line following solution? Introducing the LF-9000 line following robot, the latest and greatest in line following technology from Group 6. We were tasked to develop an original line-following robot to compete in a competition where the robot must negotiate a course accurately and with controlled speed. It needed to be self-contained and use a safe and stable power source. Budgetary constraints and advanced functionality criteria were also considered. Any number of robots could do this. We think our solution is the best.
Hi, I'm Vincent. I'm responsible for circuit prototyping and mechanical design. I worked on the sensor array prototype with Lachlan and the power circuit with Terry. Also the whole mechanical design of the chassis with Robert. I also acted as quality assurance as I worked with everyone. I could easily and quickly identify if there were problems with systems integration. We started with a large square chassis, which worked, but after expecting the movement and the power and the shape, we decided to reduce it to a triangular zero turning system with a caster wheel in front, providing easy control and maximum maneuverability. Circuit prototyping consists of finding the best resistors and capacitors for our design. To solve this problem, we used a potentiometer to determine the resistor value, which would provide optimal sensor outputs over here. And capacitor values for regulator power supply was calculated and tested.
2 printed circuit boards are required for this design. They include the main board mounted onto the top that contains the microcontroller and the inputs and outputs for peripherals. And also fixed to the underside of the chassis is the sensor board. The sensors have been spaced optimally to detect the 19mm wide tape with contrasting colours to the background. The main board includes the microcontroller, which slots into headers. This design choice was made because it's simpler to replace the microcontroller if damaged. There are also other headers that break out the pins for easier access for prototyping. Another feature on the main board is a separate 5V regulator that can draw up to 1 amp. This is required for the power supply to the sensors, but can also be accessed by these 2 headers here.
Hi, I'm Robert. I was responsible for the mechanical design, prototyping and testing. We started off by testing the motors for their speed and torque, and then we built a cardboard prototype with a slider at the front instead of a ball bearing. Originally this used 4 AA batteries, which gave us 6 volts, but we placed them over the back axle, which led to weight problems, which gave us wheelies. This showed us how important weight was. So for the next full prototype, we balanced every component properly by putting a lot of things in between the axles. Also, we're going to go with a 6 battery 9V setup, which at the moment is on top, but we will put underneath using a thinner battery pack, which can be located just slightly forward of the axle to give a better center of gravity.
I'm Lachlan and I'm responsible for project management, circuit design and prototyping, systems integration and programming. I worked on sensor circuit design and prototyping before handing off to Terry for PCB design. Many sensors were considered and tested, but we found that these ones were the best because they're cheap, robust and work well over the required distances. Systems integration required working with the team to develop a SolidWorks model of the chassis with all subsystems and components mounted. All team members provided details on their individual subsystems, and then I worked on developing a final coherent model that brought all of these discrete subsystems together into a final product. This resulted in the LF-9000 prototype, which you see here. The main challenge with programming was determining how to use registers, but after some research and testing to confirm that these were working, some simple control logic could be implemented for line following.
This project was managed using the Scrum method. The product backlog was developed with a list of features to implement, and for each, interdependencies and estimated completion time were listed. This allowed them to be ordered into sprints, which we complete each fortnight by assigning features to be implemented. Group meetings occur 3 or 4 times a week to track progress. The burn down chart created with this data shows we are making good progress with an expected completion date around the start of week 11. The project budget is managed to keep costs to a minimum. The most expensive component is PCB printing. At this point we have over a third of the total budget remaining and more than 80% of total project costs are accounted for. We expect the final product to come in at around $70 to $80. In the coming weeks we will implement improved control algorithms, sensors for speed and stop zones, and optimize the mechanical design for balance, speed and acceleration.